time, I think. Yep. Anyway, okay, so off we go. Well, there you go, Claudio.
Okay, so thanks, Piers, for the introduction and for the invitation. The first thing I did when I entered the car today to drive to the office to give the talk was call a good friend of mine who lives in London, telling him that I'm giving a talk at a conference in London, but today I want to stop by to visit him. And hopefully by next year, this idea of virtual conferences will be a thing of the past. Well, at least it will be good for the students, but at least some of us would like to see our colleagues in person. But anyway, so today I'll talk about fractal topological order, which is a rich topic, and what I'm hoping to capture with this slide with fractons in the middle is that it touches many topics, current topics, in theoretical, I would say physics, not just condensed matter physics, because this also captured the interest of field theorists. But it touches many corners, like topological quantum glasses, the idea of quantum memories, how to retain quantum information. Answering the question, can you retain quantum information at finite temperatures in dimensions less than 4? Topological order per se, foliation, higher rank gauge theories, multiple algebras, and the fundamentals of quantum field theories, generalizations of Chern-Simons and BF theories, and even elasticity. So here it's a topic that many people worked on, and here I just select a few of the players who made important contributions. So I would say that the topic started with this idea of answering whether one can have a quantum glass without disorder, that you could actually an exactly solvable model that you could show that you could not reach the ground state as you cool the system to 0 temperature. And it so happens that it is also an example of a topological quantum spin liquid. Then quantum memories, all the contributions from Bravi, Lewis, and Terhal, and Ha, with a very important contribution. Then the topic really picked up after a paper by Vijay, Ha, and Fu that connected this to generalized gauge theories, and actually classified and called these fractons, and classified them into 2 types. Then there were questions raised of how to go from these exactly solvable models in the lattice, and how to understand how you could deform these models and put them in surface of different genus, and the ideas of foliation. Then the understanding of why you didn't have mobile excitation. So in a way, maybe you can say, okay, fractons are systems where your particles don't move, right? The elementary excitations, but dipoles or 2 particles could move in the certain types. And this was made very clear in the continuum by these ideas of Predko, and then Beaumash and Barskelly as well. The ideas of the multiple algebra by Gromov, how fractons challenge our notions of quantum field theory because of this UV-IR mixing, and that's the direction pushed by Seiberg and Schau. In the generalization of Chern-Simons theories, the work of Slago and Kim were the first ones to write a continuum field theory for these fractons. And other works like the one by Yu, Devaco, Sondi, and Burnell who tied this to Chern-Simons theory, and reaching out to very interesting ideas by Radzichowski and Predko that fractons could also describe topological defects and within the theory of elasticity. So I won't be able to touch on all the topics for two reasons. The first one is the time, and the second one is that some of these topics, they're better qualified people to discuss. So I suggest as a topic open for future meetings. So I'll focus on the topological quantum glasses. That will be the contents of this first talk, in topological order. And in the second talk by Wesley, he's going to discuss continuum field theories that, and I'll focus on the lattice today. So a lot of these ideas here, they are actually contained in written form in these lecture notes in Trieste Summer School. So those interested in looking for something that you can actually flip the pages, I suggest looking at these lecture notes. They were in 2009, perhaps a little bit ahead of their times, and the topic stayed dormant for a while. But let me get to what the fractons are. Let me take a route that is, I'll start with an example, not of fractons, but that will give us a flavor of what is that, what are the ingredients, what is involved in these, forcing the particles not to propagate. So I'm going to take an example as a warm up, which is the When plaquette model, which is also tied to the toric code. So this model is defined on a square lattice, and we tilted it 45 degrees here. The spins are placed on the sides. And the square lattice, we're going to define black plaquettes and white plaquettes. It's bipartite. And whenever we're going to compactify, we're actually going to take, even by even compactification, so we can really retain the black and white plaquette structure. We define operators on each of these plaquettes. They're the product of the four spins on the corners. Let's label them in a very intuitive way, which is, since we tilted this 45 degrees, we're going to have the spin on the east side, the west, the north, and the south. And along the north-south line, or the y-axis, we're going to put a sigma y operator on those sides. And along the x-axis, we're going to put sigma x. Similar, the exact same thing for the white plaquettes. And we're going to define the operator on the plaquette as the product of these four spins on the given plaquette. Now, these plaquette operators, they all commute. So if I take two plaquettes, P and P prime, either they are far away plaquettes that don't share any spin in common, so they will trivially commute. Or if you take two neighboring black plaquettes, they will share one spin. That would be, say, a sigma x here in this geometry, or they could share sigma y if they were touching one on top of the other. And if you take a white and a black plaquette, they will share two spins. Now, sigma x and sigma y don't commute, but you pick up two minus ones as you commute one plaquette operator past the other. So we're going to pick up two minus signs, and therefore minus 1 squared is 1. So the two plaquettes will commute. So we have a set of commuting plaquette operators. You can define the Hamiltonian as the sum over all plaquettes of these plaquette operators. And you put a coupling constant lambda in front and the minus. So since these plaquette operators, they square to 1, you have eigenvalues plus or minus 1 in each plaquette. And the ground state will be the state where all the plaquettes have eigenvalue plus 1. Now, a first naive counting, well, you have as many plaquettes as you have spins on the lattice, if you had taken an infinite lattice. So you account for every degree of freedom. So you will have a gapped system. This is pretty much like a paramagnet, right? And your gap is equal to 2 lambda, the difference between flipping one plaquette having eigenvalue +1 going to eigenvalue -1. But this is not quite the full story, because if you put the system on a torus, and if you multiply all the black plaquette operators, you get 1, because if you go around every black plaquette, every spin is shared between 2 plaquettes. So if I multiply here the sigma x, there's a sigma x coming from this plaquette, sigma x coming from this plaquette on the right, sigma x squared is equal to 1. And similar to all the corners, when you close it, these plaquettes multiply to 1. And you can do the same thing for the white plaquettes, and you have 2 constraints. So in even by even lattices, the Hilbert space is just 2 to the number of spins, and the number of spins equals the number of plaquettes. But now the number of independent plaquettes are just the number of plaquettes minus 2, because you have 2 constraints. So let me see if I can move the zoom bar without doing any damage. Okay, so it was covering here the degeneracy. So, well, 2 to the NP, the dimension of the Hilbert space, is 2 to the number of independent plaquettes. We're missing a factor of 2 square. That's the degeneracy. That's the topological degeneracy of the system if you put on the torus. That can be resolved by adding a couple of operators that will commute with all plaquettes, but they will be non-local. And they resolve this topological degeneracy. In this example of the one plaquette model, they're just products of, for example, sigma y operators along this pink line. And the pink line will cut, say, a black plaquette here in 2 points. Along the horizontal axis, you have sigma axis, but you have 2 of them. So this operator will commute with this plaquette. Will also commute with the ones that it touches on top, like this white plaquette over here, because this line contains a sigma y, and the plaquette here at this point has a sigma y. So these non-local operators, they will commute with the Hamiltonian, because they will commute with all the projectors. And these non-local operators resolve the degeneracy on the torus, this topological degeneracy equal to 2 square in the even by even lattices. Now, this model is closely related to the toric code, and to see that, if you break the spins into 2 sublattices, the sites where the spins sit, you break it in 2 sublattices, a pink one and a blue one. And you take the blue sublattice and you rotate the spins by 90 degrees. So you take a sigma x goes to plus sigma y goes to minus sigma x. And if you do that, the black plaquettes will then contain only sigma x operators. And we're going to just redraw the lattice, like we're going to put this little blue square or bigger plaquette around the black plaquette. And around the white plaquettes, you define the star, the pink star here. And there, you'll have sigma y operators because of this rotation. So you recognize that this is nothing but Kitaev's toric code if you have an even by even lattice, because then you can then basically take your black plaquettes become your, the plaquettes of the toric code, and the white plaquettes become the stars. Okay, now we're gonna get to the motion of the excitations. So let me start first with the usual excitations that we have in these in the Venn plaquette model / toric code. So suppose you take a spin on the lattice and you apply, say, a sigma x operator. Now this operator will commute with 2 of the plaquettes, say the black plaquette, because it has a sigma x on that corner, but it won't commute with the 2 white plaquettes because those have a sigma y. So what you do is you create 2 defects, you create in pairs these 2 defects, and we're going to draw a little string between these 2 defects. So the effects can only be created in pairs. Similarly, if you apply a sigma y operator, you're going to create two defects on the black plaquettes, and we're going to paint them in blue with a blue string connecting them. So if you apply either a sigma x or sigma y, you're going to create defects in pairs. And you can move around these defects by applying more sigma x and more sigma y operators. And in particular, if you have a certain configuration, you have a couple of blue defects here and pink defects. If I take this blue defect and start flipping things around, and wind it around the pink defect, the blue string and the pink string will cross. And at that crossing, the operators that create them don't commute. One is a sigma x, one is a sigma y. So you pick up a phase of -1. So there's mutual statistics between these particles. And I mention it here because you can actually understand at one point when we start taking the continuum limit, which we're not going to do today, but you can show that the continuum theory describing these models is a double Chern-Simons or a BF theory, and that this mutual statistics is contained in that continuum limit. But that's not taking us in the direction of the fractals. So now let's look what happens if instead of applying a sigma x or sigma y, you apply a sigma z. Now, sigma z won't commute with the four plaquette operators that share that spin. So you're not going to create just a pair of excitations. You're going to create a quadruplet. So you're going to create the two pinks and the two blues. So the essence as to why we're going to get excitations that cannot move is that we'll construct models in which this is all you can do. It's not quite true. Well, it's definitely not true in the when plaquette model because you can create string excitations. But let's play a little further with the model, but applying sigma z just to see what would be the consequences of just generating defects in quadruplets, not in pairs. So first thing is that, okay, how do you move defects? So suppose you have an isolated defect that's sitting there, for whatever reason, like, if you go back to the Hamiltonian, it's that of a paramagnet. So if you're at a certain finite temperature, there will be a density of defects, and then, well, here's one. So how do we move this defect? Well, if you flip the spin, you're going to flip the four plaquettes. So you're going to heal this one, and you're going to generate three more. So you went from one defect to three. So before this costs energy delta, now it costs energy 3 delta. You have to go over a gap, an energy cost of 2 delta to actually do this move. Now let's see what happens afterwards. Well, you paid the initial, down payment of 2 delta, but now after that, the dipoles can move freely, because if you flip a spin here and you flip the four plaquettes, you go from 2 defects to 2 defects. So there's no energy cost. So once you pay that initial penalty, you can move the defects, the dipoles, the pairs, freely. Okay, so that gives us our first taste that a single excitation cannot move, but 2 excitations can move. And so that's what we say here, right? The dipoles can move. Now, let's look at the problem of removing excitations from the system. So suppose that you are in equilibrium at a certain temperature, you want to reduce the temperature. In particular, suppose you want to take the system to 0 temperature and get rid of all defects that you have. Well, so suppose that you have initially 4 defects, like in the corners here, the green ones. So let's go to the picture on the left. So if you flip this spin here, you're gonna heal this defect, move it here, give this hop, but you're gonna generate this dipole. Now, once it's generated, dipole can propagate to the other end, come close to the the defect sitting at this corner, and then you can heal these 3 defects, and you're left with one defect. So you basically move these defects along this line, right, by 1 notch here in this direction, but you had to pay an energy cost initially. So this is what we call sequential move, because you have a barrier of height 2 delta, and you have to first go above the barrier, and then you sit on this mesa, and you just travel to the other side, and then you heal, and you go back to low energy situation, at least same energy that you started. And if you were to remove all the effects like this, okay, well, we just have to go over these speed bumps, right? Now, suppose instead you say, well, what about quantum tunneling, right? Well, this is an example where tunneling is worse than going over the barrier. Because, well, let's do one move that gets rid of all defects at once. So you could flip all the spins in this region, or this, let me call it a membrane, where the green spins are at the corner of this membrane. So if you flip all these spins, you're gonna heal it, you're gonna get rid of the defects. But this is a process equivalent to going under a barrier. And in perturbation theory, this scales as the area of this membrane. So it's highly suppressed. You could do a little better, which is instead of flipping all of them at once with the area, you could actually just mimic what we've done here. We flip these spins. So you would have the net effect of moving the excitations 1 notch here and there by flipping this string. But again, in perturbation theory, the amplitude scales with the length of the string, okay, which is the width of the barrier. So it's exponentially suppressed. So if you ask what is the relaxation time, how long will it take for this process to occur? Well, in the sequential one, you have to wait for a fluctuation that will take you, kick you by energy 2 delta. So you do have for the transition amplitude, you are suppressed exponentially, right, in an Arrhenius fashion. Now, if you're hoping to do this through quantum tunneling, the process will take some whatever coupling to the bath is, divided by the gap, raised to the, well, here we use the area, but you could also have used the length and do this, part quantum tunneling, part sequential, or a sequence of quantum tunneling events. The difference is that you would replace this distance here squared by a distance, and still you're going to have a double exponential, right? A suppression of your switching amplitude. At a temperature T0, the typical distance between your defects will be C, given by just the inverse density, right? Square root of the inverse density. So the width of your barrier is growing exponentially as you reduce the temperature. And in particular, if you take the temperature to 0 and you kill the sequential processes, pretty much the closer you get to the ground state, the lower your density of defects, the longer will take to get rid of the next step in this hierarchy of removing the defects. So this is extremely slow. So in other words, you have that the quantum relaxation shuts off as a double exponential of the residual temperature. And then even if you have an interesting, topological quantum spin liquid there, you would never get to the ground state if you actually reduce the temperature to 0, right? You would wait forever. And if you reduce the temperature gradually, you will have this Arrhenius relaxation.
Claudio?
Yes.
Why do you call it quantum relaxation? It involves the temperature. Surely it's thermal relaxation.
Okay, so I didn't want to take the temperature all the way to 0, but suppose that you actually quench it to 0 temperature and you have a 0 temperature bath. So the bath can still take energy out, right? So that if you start with an initial density of defects at the early stage, now you have to wait for your bath at zero temperature to get rid of the excitations. But if you go to zero temperature, you really kill the sequential relaxation. So the only thing you have left is quantum tunneling.
Okay.
So if you go back to this picture, you know, these things they're kind of frozen because, if you actually have a quantum tunneling process that will remove some excitations, you're left, the ones that are left, they're even further apart. So it will take even longer. And then, and so on and so forth, right? So the fewer excitations you have, the longer it takes to get rid of them. So,
okay.
yeah, it's an example that it doesn't matter how low the temperature is, like, you know, the kind of a classical going over the barrier always wins over tunneling. Okay, now we do have a problem that, well, that model we applied sigma z, but that's because, you know, we chose, the rule is that the bath can apply anything it wants, right? Whatever is not forbidden is allowed. So one can apply sigma x, sigma y, and then you're gonna move your strings and nothing like that will happen in this model, and it doesn't happen in this model. But playing with this 2D model gave us some intuition of what it is that you need to do to kill the, you know, quasi-particle excitations that can be created in pairs, and you have like strings connecting them. You have to create them in quadruplets. Now, so we, you know, it won't work in 2D, but there's an example, right? If you go one dimension higher, and you generalize that when model and construct an FCC lattice and put your spins on the sides of the FCC lattice. And we're going to define an operator, projector operator, that has only not only the product of sigma x and sigma y, but you're going to add the sigma z as well. So to make life easier, let's redraw that plaquette operator. And let's just redraw it like this, like a little star, because you can think about, we had plaquettes and the spins. You could imagine a square lattice where you put your plaquettes, and the square lattice that you put your spins, the original one. So it's basically, you can think about a bipartite lattice where, you know, half the sides were your plaquette operators, drawn here with a big circle, and the other half are the spin operators. And then that makes our life easier to think about that FCC lattice, because you're going to have to find these octahedra operators in one of the sublattices of a cubic lattice. And the spins were going to be in the other sublattice of the cubic lattice. And in that way, we're going to have still east, west, north, and south, and we're going to put the same components that you put in the Venn plaquette model, sigma x, sigma y. But now we have top and bottom, and we're going to put sigma z on the top and sigma z on the bottom. So now we have the product of 6 spins, and we call these the octahedra operators. These are projectors. They square to 1, just like the plaquettes. And the commutation relations we can check. They are commuting projectors because they either touch along one direction, so they will have the same component of spin when they touch like this, in these little stick figures that look like those assembly instructions in the IKEA furniture. So they touch on one spin, they commute trivially. And if they touch along a plane, right, they're going to have different components, but just like in the plaquette model, you're going to have 1 minus 1 coming from the commutations on this side, and the other one minus 1 there, minus 1 squared is 1. So these operators commute. So we can now, for any octahedra, these operators commute. So we can build a Hamiltonian, which is the sum of these projectors. sum of commuting projectors. And you can also count that you're going to have as many octahedral operators as spins, because they're just the two sublattices of this smaller cubic lattice with the smaller unit cell. So it's a solvable model of a gap spin liquid in 3D. Now we can do we can count the degeneracy, and the degeneracy will be at least, if we find those sets of operators that multiply to 1. So for example, this lattice, the FCC lattice, has 4 sublattices. We can call them A, B, C, D. And if you multiply all the operators in one sublattice, you get 1. So therefore, there are 4 constraints, and because of these 4 constraints, your degeneracy would be 2 to the 4. And here, at least, because in the next couple of slides, we're going to discuss this more carefully. Now, the one thing that already points that these models are different, right? They're a bit strange, is that, or something that signals that you don't have string operators. That if you do have string operators, you think about you create excitations that live at the endpoints of the string. You take around your Tor, 3 Tors, like if you put periodic boundary conditions. So winding these strings around the whole system and recombining them will give you some operation that would flip your ground state if you had strings. But if that were true, then you would expect that you have such a thing in the X, Y, and Z directions, which means that your degeneracy should be a cube of some integer. And 2 to the 4 is not the cube of an integer. So this number is already, it's strange in this sense. And this is tied to, well, maybe a simple resolution is that you won't have those strings. You won't have the particles. Okay? So that's a strange degeneracy for a 3-dimensional system. And okay, let's check that in this model, we're safe that you can apply any operator that you wish. You only have like sigma X, sigma Y, and sigma Z. And if you apply this operator on this site, then here there are like the 6 octahedra that touch this site. So in this case, say you apply a sigma Z, the octahedras on top and the bottom will commute with this operator, but the other 2 don't. So you're going to generate 4 defects. If you apply, say, a sigma X, the 2 red ones here will commute, but the blue and the pink will not. So you're going to generate 4 defects. And you can check that it doesn't matter what you flip, you always flip 4 octahedras. So you create defects in quadruplets. So you cannot have an operator that will, create a pair of particles or move a pair of particles. So the motion that we described before, that dipoles can move, that remains, right? Because if you flip a quadruplet, you can always take 2 members of that quadruplet and flip a spin, close, another spin, and you're going to move 2 of those excitations. You can move by a little bit. So you can propagate the dipoles, but you cannot propagate the single particles. And I said that the degeneracy was at least 4, but it's more complex than that. Actually, Bravi, Limhus, and Terhal proved that the degeneracy in this model can be written as the greatest common divisor of the 3 different directions, right? And so it's an issue of commensuration here. Greatest common divisor is, it's not very common that we find this in physical systems. That points to commensuration issues, but it also points out that the system, if you're looking at a property that usually topological degeneracy, we think, okay, that's a property that you can take to continue, limit it, and understand it. But here, the lattice is there in the background. right? This is part of these problems with infrared ultraviolet mixing, that you cannot forget completely about the lattice. So in any case, there's a simple case when they're all equal, so the greatest common divisor will be L. And this degeneracy scales sub-exponentially with the system size, right? 2 to the linear length of the system. So that's very different than the usual topological order, right? The kinds of topological order that we encounter, say, in the 3D toric code, or in all the two-dimensional ones, like the ones we encounter in the Cohen Hall effect and the toric codes or double models. And again, the dipoles can move freely, but elementary excitations, the single excitations, cannot. In particular, if they cannot move, they cannot move and they cannot turn corners. So, and for the same reasons that we discussed in that toy example that we suppressed, the bath could only act with the sigma z when we discussed the Wen plaquette model. And here, it doesn't matter what the bath does. If you quench to 0 temperature, you're going to be stuck with these defects that the closer you get to the ground state, the longer it will take to go to the next level in the hierarchy, right? The further away the defects are, and you can measure the distance to the ground state with the density of defects. And so the more sparse they are, the longer it takes to get rid of them. So it's an example of a system that you have like these interesting, ground state properties, like the topological degeneracy, but it will always have like defects that, frozen in. Now, there are other models, and in here I'm kind of going through the, how we reach these types of systems with these constrained dynamics. So that was the first example, but there were other models, like for example, in these ICTP lectures, we had this model that had a fractal membrane. So which is built, kind of similarly to that model in the FCC lattice. You build these prisms with 5 spin operators, product of say sigma x on the plane, and you have on the top and the bottom you apply a sigma z. These are again commuting projectors, and you can create excitations, and you can separate these excitations by flipping, for example, the spins that are schematically drawn here as red. So this is an example of a fractal membrane that if you flip these spins contained within this gasket, you're going to have excitations at the corners of this membrane. Now, this model is quite anisotropic. The excitations can move in the z directions freely. So they have restricted mobility that qualifies them as fractons, but they cannot move on the plane. Okay? That would, that requires a major rearrangement. You cannot move before creating more. Now,
Claudio, can you define for us what a fracton is? I mean, how is it different to other fractional excitations, emergent particles?
Okay, so the working definition of fractons now is that it has the elementary excitations cannot move, and then you branch into 2 classes, the type 1 and type 2, and which is funny to say because I'm presenting a type 1.5 here, but there's type 1 that the elementary excitations cannot move, but dipoles can move. Okay. And as opposed to the usual, fractionalized systems, like for example, the fractional Cohen Hall effect, your quasi-particles, you can move them around, right? Once you create them, you can move them around. So you can describe them, in the usual field theories, you have some effective theory that has particle excitations, and these particle excitations they can acquire mass, and you can move around. So in the definition of the fracton is that the elementary excitation cannot move. But dipoles or multipoles, it could be the case that you could cook up something that maybe dipoles cannot move, but quadrupoles could move. Okay? So that would be a type 1.
And the localization is not driven by interactions, but driven by topology or
no, actually here it's more like a kinetic constraint. So it happened that at least for the gapped models, they are topological. And here I'm only talking about the gapped models. Mm-hmm. But if you go back to well, even though the examples that we found are examples of systems that have a topological degeneracy. Let me go back just a little bit, because this point is, there you bring in is important, right? So here, it's more like a kinetic constraint, right? That we define this, we define a lattice model with we put the, we define operators and they're commuting so we can solve for the exact ground state. But what gave these funny properties is the fact that once you have these operators and you ask, okay, how do you create excitations, right? So if I take the ground state where all the O's have eigenvalue +1, and this is a spin model, right? So I have to think about any product of any local operator that I can apply to a site and see what happens. Think about it in perturbation theory, right? I turn on some perturbation and I want to know what that does, right? So here the perturbation would be, say you apply a field in the x direction. But when you apply the field and you see, okay, well, you're going to create excitations because this field that you applied doesn't commute with your operators you use to write the Hamiltonian. But that operator will never create just, never creates one excitation. That's very common to these topological systems, that you create them as endpoints of strings, right? You create them in pairs. But here what's different is that not even that you can do. When you create excitations, you always create them in quadruplets. And it is, here I would say it's a kinetic constraint, right? It's a geometric constraint that in the way that we define the lattice model, you cannot escape this, right? That because you basically used all the components, you exhausted all the components that you could use in defining this operator O. There is no way that you can create just a pair of excitations. So it's really a geometric kinetic constraint.
Okay, thank you.
So, in principle, like, for example, the systems that Leo Radzihovsky found in, those are elastic systems, right? So it doesn't even have to be quantum, but it has to be, in a way, you have to, the way I like to think is that we corner the system. So by going to taking that 2D model and going to 3D, basically we corner all the possibilities. So the system, there's nothing you can do. You can only create this excitation in quadruplets. Now, one thing that it's good to mention at least for these systems, they are gapped, and is that you could, then you're even protected by the gap, right? Because if you apply this, if you apply perturbation, yes, you can create these excitations, but you won't go away from that phase, and you cannot change that degeneracy. That's another issue. But yeah, so in other models, for example, you can have even stronger constraints, like that's this example in the. But here the particles can move freely along the z direction. But even then, you could say, well, they can move freely, they can annihilate. But if they can move freely, though, they're only created in pairs. So the parity of the number of excitations at the corners of these gasket, that is conserved. So you can move it freely, you can generate pairs, but you can go from 1 to 3, but you cannot get rid of this thing unless you eliminate the 3 of them. So in this sense, you have, if you actually ask mod 2, I would say this is a type 2 fracton. But maybe a 1.5 is a better definition. But a real type 2 is this very rich model by Ha, that here he defines the model in a cubic lattice, and he use basically double the number of degrees of freedom in the side. So he used basically 2 spins, a tensor product of 2 spins. And in this notation here, X is this is a sigma X times an identity for the other spin. And he has 2 types of cubes. One has X components, the other one Z component. And this model is such that when you try to create excitations, right, you can actually create 4 defects, which are the corners of this fractal object, right, fractal pyramid. And these effects are frozen because you cannot move them without creating more defects. So this is an elementary, well, it's an excitation that will cause 4 times the gap. But once you leave them in place, they just cannot move without creating more and more. Basically, you have to, one way to get rid of these 4, like you could flip things that would heal this guy and put 3 more there, and you do hierarchically, right? But these are, so one way to say that, these are very unusual beasts, right? Not the usual things that we're used to, even as we get more and more used to by now, okay, so many years after the fractional quantum Hall effect, we get used to it, right? It becomes familiar. But some of these models are still, we're still learning about them. So another model, which is it's very useful. It's kind of like becomes almost like the hydrogen atom, the harmonic oscillator, is the X cube, because it's simple to write. So this was introduced as the X cube by V.J. Ha and Fu, and it's a bit similar to the way you define, say, the torical. Here you can take stars, and then you have the product of sigma z's around stars, and there are 3 types of stars in this cubic lattice, and you define a cube operator with 12 products of 12 spins that will flip these stars. And that's an example of a type 1. Your excitations can move along, you have restricted mobility along certain lines. I should mention that Claudio Chamon reminds me that we did write exactly the same model in an appendix of a paper we wrote with David Sherrington, but our goal is totally different. And so we're also looking at some glassy systems and actually try to use ideas of, can you define can you use the ideas of entanglement to define a transition that has no thermodynamic signature. So that didn't, so we went into the appendix because it didn't quite fit the main topic. But that is to say that there is a close relationship between these models and the difficulty of equilibrating if you study them from a dynamical perspective, not just the spectral properties. Now, I call this the end of part 1 because this was all in the lattice before we dive in the continuum, but the continuum will be the topic of Wesley talk. So I can either go further and start going in the direction of the continuum, or we could take questions. So this is a good branching point.
Yeah, I think it's a good point to take questions. So yeah, can I invite questions from the audience? Okay, Kadan has a question.
Yeah, so this is a little bit technical, but I'll try to describe it. So you talked about these string operators for the models that you're introducing here. I guess what I'm wondering is if I perturb these models, I do expect these to be stable phases, but can I still think about having the same string operators, or do the string operators get perturbed somehow? And if so, do we know sort of how to construct those or what they look like?
Yeah, but the string operators, you actually lost them, right? The string operators are things that connect the quasi-particle excitation. So for the models which are not fractons, like say the toric code or the 3G toric code, the 3G toric code has two types of excitations: membranes and strings. So the systems that have strings, you can always like stretch create create these quasi-particles that you should think about. The string is kind of like, well, the quasi-particle lives at the end point of that string, because at the other end point, there is another quasi-particle. But in these systems, you actually have, the right way to think about it is that you create quasi-particles in quadruplets. And, there is this little kind of like, think about them as the corners of some tiny plaquette. And the way that so for example, a dipole is like you have a tiny plaquette, and you add the little tiny plaquette on the side, and you kind of stretch, and your excitations are always at the corners. But it's just because you put your tiles like, just one row of tiles, very, then you're just going to have two dipoles at the endpoint. But maybe a better way to think about it is that these excitations live at the corners of these membranes.
So okay, so maybe string operator was the wrong word, but is there not an analog of using the membrane operators in the fracton phases to diagnose them?
Yeah, I think you can use the membrane operators to diagnose, because actually one way that you can construct the, let me go back to here we just counted the degeneracy in a naive way by looking at the, to 4. Yeah, here. So you counted the degeneracy only by counting the number of constraints, but you can actually construct these kind of membrane operators that go around the whole system, and so in that sense, you can characterize this degeneracy by eigenvalues of some membrane operator. So that still exists.
Right. So then my question was that membrane operator that counts the degeneracy, that's specific to this model. Now, presumably the phase is stable if I perturb the model, but I would guess that maybe I wouldn't be able to look at the same membrane operator. It would get deformed somehow into some other membrane operator. I don't know if this makes sense.
No, it makes sense. It's just like it's the same question as a kind of in the topological system. You could apply the same thing to the toric code, right? You construct a string operator, but if you perturb that string operator, you can have a transverse field, and now you don't have a system that is a sum of commuting projectors, right? So let me think. Yeah, that string operator that you define to look at the topological degeneracy, that operator, I think, may not commute with your Hamiltonian anymore, but you know that you still have the degeneracy, right? Because as long as you don't close the gap. Yeah, as long as you don't close the gap, you don't have any local operator that would connect these different sectors. But now the notion of maybe it could be even a dress string operator, but not the original string that you used, right? Yeah, case in point.
I mean, somehow maybe this is incorrect, and this is sort of where I was getting with this, but I was thinking that maybe you would actually need something like a matrix product operator to describe the string case. And then for the fractons, it wasn't clear to me what the analogy of that would be to go to constructing the membranes, right? But anyway, I think your answer was very clear, so thank you.
Mm-hmm. Yeah, one thing that let me volunteer a comment maybe before the next question. You know, of course, what I presented today, that's kind of like you know, how to build these things from as an example, right? And we start from the lattice, and a lot of the more recent developments went off lattice, right? I think kind of there's still interesting things on the lattice, but we're kind of graduating away from the lattice. But the one thing to be sure, Mike, is that these are theoretical concepts, and you could ask, okay, how close are we to any experiment? And I would say, well, we're far, because in any case, there is a backlog of things that one should do before getting to the experiments in this, including realizing the Z2 gauge model in the lab where you can measure, right? Like an example of Z2 spin liquid in the lab. So it's kind of like we have so much work, a backlog of work, but that eventually one could get there. So because at this point, there's a lot of concepts, you know, this idea that, yeah, you don't have quasi-particles are not moving, right? So here's an example of systems without mobile quasi-particles. They are there, you can define them in the spectrum, but they cannot move. So these are my 2 cents about how far we are from experimental realizations. Although there has been some proposals in 2G by Pratko of how to use a doped kind of classical classical in the sense of not classical, but the anti-ferromagnets with the only ZZ interactions. And but I think we're still quite far from that.
Before we go on, maybe I can ask a question. I guess you've talked about the toric code and the plaquette model, which I guess are unitary transformations of each other. But the toric code is a limiting case of the Kitaev honeycomb model, where limiting case which is gapped. Is the same true of your 3-dimensional model? Can that be written? Is that a limiting case of a corresponding 3-dimensional kind of Kitaev spin model?
I don't know. I never thought about it, Piers. It's actually a very good question, right? In the kind of in the honeycomb, like Kitaev exhausted all the direction, had the XX, YY, and ZZ. But
right, and he made one much stronger than the other 2, or something like that. Took him to a toric code, right?
Yeah. So here we need. I don't know. I hadn't thought about it. It's actually a very interesting question, right? If there is
know the answer to that in the audience, I don't know.
Yeah, I should say that.
This is Young back.
Young,
what do you think? Yeah, hi.
Claudio, great talk. I really enjoyed it.
Thank you.
So, Piers, there is a related work actually. So, Kevin Slagle, when he was a postdoctoral fellow at Toronto, we constructed a related model. It's not a Kitaev model, but the model inspired by the Kitaev model. So it's something like a stacked version of the 2-dimensional Kitaev model. But in that case, you can construct essentially a 2-spin exchange model. Then when you take some anisotropic limit, just like what you described, it actually, the entire the model can be made to an XQ model. So there's some version of that, but it's not quite the same as the 3-dimensional Kitaev model. But there is some twisted version of it.
Thank you. Oh, great to hear from you, Jan-Beck. Wonderful. Okay. Other questions? I'm hesitant to take you into the next lecture because don't you have your isn't that going to be given by
Yeah.
your student?
Yeah,
Right?
but I could just give us some intro, and of course, like, but let me, well, I promise I won't go too far, but yeah, but just to motivate, right? Because
Okay, great.
everything I talked about was on the lattice, and for a while, I have to say that back, this was many years ago, right? And it was the field was a little lonely. And then it takes a community to, when the community comes in, and then there's like the richness of ideas, like it really helps. But back then I was like, oh, this is too strange, right? So how can you even have a field theory if you're gonna move your particles to at least the ones that I knew, like the particles could move, right? Other things had the theories of membranes, but then he understood, okay, well, describe the strings at the boundaries of open membranes, but these things that cannot turn corners, and even like that type 1.5 that had this Fracton membranes, it seemed really weird, and it seemed that okay, these are things on the lattice, and so I really questioned whether there could be a field theory, and but the answer is yes, and was actually the work of Slago and Young Beck that was the first work that showed that you could construct a field theory, and they did it for the X-cube model. And I think that what this work did is like it really opened, because before it seemed that, okay, this is within the confines of condensed matter physics because it's all on the lattice. And by opening up, not only, okay, well, we have our interest in condensed matter in the field theories, but it also, created interest within the field theory string community, because now you have these field theories for these rather strange models. And since the work of Slago and Kim, there was much progress, right, in different directions, and I list here just a few. And the one that Wesley is gonna talk on Wednesday is again, like, you cannot go over all of them, but he picks up one, which is the direction of writing these as Chern-Simons and BF theories, because. And then we actually took this and wrote generalizations of fractons in higher dimensions, because also there's a lot of work then in 3D, but I show, okay, we can make this at least within this construction to any even dimensions. And again, yeah, I'm sorry, this field is still in a stage that is more abstract. It's very interesting, very rich theoretically, but I think it's one of these things that's way ahead of experiments. But again, we do have a backlog, right? We have to create a number of spin liquids and probe them, and maybe engineer them in quantum devices. So there's a backlog of work for us. So maybe I could stop here, or I could do something that I'm not sure that Wells is going to get, is that as a warm-up, the same way I did the warm-up with the Wendt-Plaquette model, I could do a warm-up in 2D with Chern-Simons theory, just to maybe prepare at least the younger in the audience for what's to come on Wednesday.
I think it's a nice idea. Before I go on, there's an entry. There are two entries in the chat. One is by Adam Nahum, who said that, which is in reply to one of the questions we had about what happens to the string operators. He says that it's related by an adiabatic transformation of the original one. I guess that's when you start to deform the model. And there's a remark by David Sherrington.
I think Claudio already did it.
Okay. And David Sherrington mentions that fracton is defined in the Wikipedia as the analog of phonons on a fractal. And he suggests that there needs to be an additional definition.
Yes, and let me touch on that. I think David is right that there's and I think I even had read some of reviews way back when, before these things were called fractal. So I think there was even a review on phonons on disordered lattice by Orbach. And I agree 100%. So the name has been abused because there's that. There's also some other context that was defined maybe in the 70s in high energy physics with a completely different name. So I should say I'm not the one who coined that. I think that it was Vijay Hein Fu, but I agree that maybe the name. Well,
So disambiguation.
well, yeah, there's ambiguation, and fortunately for physicists, we don't have copyright laws, right?
Yes.
But yes, there is there is ambiguity, and
So you can make a start now, or you can leave this open territory for Wensley. I'll leave it up to you.
yeah, let me just take a look. See,
Is there a natural?
yeah, no, I think. Yeah, I think I'll stop here because I don't want to rush and
I think that might be a good thing.
abuse the audience. Yeah.
Mill over things. In that case, if there are no further questions, are there any further questions? Any further questions? Okay, I think we're going to give Claudio a great big hand.
I'll ask you a question, I think.
Okay, go ahead, go on. Good.
Hey, Claudio, excellent talk. Thank you. So it looks like, I mean, there's all these models and they're sort of not very similar, right? I mean, is there some notion of or understanding of sort of different universality classes of fractons emerging, or are they all sort of the same thing? What is the classification of fractons? Do we have some grip on that, or is it just sort of still branching out in too many directions?
Well, I think the kind of classification has been converged at least in these two types, right? And let's say, okay, well, we could say they're fractons with the gapped and gapless, right? But I think that the classification so far, in the broadest would be in just these types, right? Type 1 and type 2. The ones with completely mobile excitations, like the ones that are at the corners of these fractal, objects, and the ones that you still have some mobility, like for example, those are the dipoles. But yeah, I think that is so far my understanding how far one can classify. There are, of course, like efforts, like Kevin Slago, like been trying these foliation approaches, right? So I suppose that out of there can be also a classification. But at least in my view, I think it's kind of early to settle on something like in the types of classification that within the same level of detail that Xiaogang aims at classifying the topological order, the usual topological order. So we still would say very far from that.
Thank you. Actually, one other kind of small question maybe. So I mean, this seems very much tied to the dimensionality of the theory itself, right? I mean, have people thought about what this might look like in 4 dimensions or even higher dimensions?
Yeah, I think we have examples. We construct them in every odd space dimensions. Mm-hmm. You can generalize, and they do look like Chern-Simons theories, at least. So, and one of the things I hope will become clear in Wellesley's talk is that this is a funny type of Chern-Simons that the number of the derivatives, right? It's not tied to the space dimensions. Okay, so for example, we can in 3D you can write some Chern-Simons type theory that it has 3 component fields, say A0, A1, and A2, but the derivatives also, you're going to have like your D0, D1, and D2. And even though you live in 3G, it's because there's some linear relation that ties that these two spatial derivatives that you have involves the three spatial dimensions. Okay, so that will leave that will become more concrete if I leave it for him to discuss, because otherwise we're kind of talking on a vacuum. But the similar structure carries to even higher dimensions. So even though these things look like Chern-Simons theory, they look like the two-dimensional Chern-Simons theories, but the differential operators can be, they are quadratic order. So there are subtleties there. But hopefully, I think that your question will become, I think, after he presents, it will be clear. That particular thing.
Excellent. Well, I'll come back to it on Wednesday if I still have questions about it.
Okay. Well, thank you very much, Claudio, and I hope you'll still be around on Wednesday when Wednesday comes back, in case there are questions to share between the two of you. And that means that's it for today from London. Tomorrow we will meet again at 2 o'clock. Karen Hazard and Frank Polman are presenting tomorrow's talks. And we're pretty good at putting recordings online. We should have those up in a day or so of today's talks. So thank you, everyone, and see you all tomorrow.
All right. Thank you
Thanks,
again.
Claudia. Cheers. Bye-bye.
Cheers.
Thank
Bye.
you.